Today we're going to talk about a model that I'm very excited about. This is a model that was developed by Ionel Dinu and is talked about in this paper, Fundamentals of a Theory of Aether, and this is part 1. And it was uploaded to ResearchGate on July 26, 2020, and I have actually given you a couple of sneak peeks of this model in a couple of my videos. So I'm going to start by reading the abstract. The necessity of acknowledging the existence of a new chemical element is discussed. A new view of the electric current as a diffusion wave in a wire is advanced. The production of a magnetic field by an electric current is explained in terms of the mechanics of surface waves. So today we're going to be focusing on this idea of the surface waves. I'm going to show you what a surface wave is, and then I'm going to lead you into the development of this model. Now you'll notice that I am also named on this paper, and this is because I helped Ionel bring his model to life with computer software, and which you have already seen in a couple of my other videos. And so now I'm going to explain what the model is and what it represents. But just as a reminder, because this is a very, very important point, in a previous video that I made, I showed you some experiments that Ionel did with spinning cylinders, and I showed you how when you have cylinders spinning next to each other, when they spin in opposite directions, they attract, and when they spin in the same direction, they repel. And so this concept is going to be become very important for the model that I'm about to explain. So what exactly is a surface wave? Surface waves are the waves that you find on the surface of lakes in large bodies of water. You find that they appear when it is windy, and on windy days the waves appear and they propagate on the water towards the shore. So here is a video I took of the surface waves at the lake that I spend a lot of time at in the summer, and you can see that the waves come in and they propagate towards the shore, and when they get to the shore they crash. So what exactly is going on? What exactly is going on with the water molecules to make these waves do what they do? So here is an animation. Here's an animation of how surface waves work. So what you're seeing here is you're seeing the interface between the air, which is up here, and the water, which is down here. What you're seeing is that when the wind blows, and I'm assuming the wind is blowing from left to right in this animation, what happens is it causes the water molecules to circulate in circular motion. So you can see here on the surface of the wave, the molecules are circulating in a circular motion, and as you go down further and further, the circles get smaller and smaller. And with this kind of motion, what ends up happening is you have a wave that propagates. So here you see a wave propagating from left to right, and what you see is that the water molecules are not moving with the wave. They're moving locally in circular motions, and the wave is propagating towards the shore. So here's what we know about surface waves. Okay. Surface waves occur along the boundary between two different substances, for example, air and water. So in the case of surface waves that we see on the lake, on this lake, it's happening between the air, which is above the water, and the water. Okay, so that's fairly straightforward, but it doesn't have to be air and water. It can be water and the sand, or it can be air in the sand. You need a boundary between two very different substances. One substance is usually lighter, less inertial, like air, and the other one is usually more inertial, more dense, like water. So what else do we know about surface waves? The deformations propagate with the wave speed. So the deformations are these surface deformations, and they propagate with a certain speed, and that speed depends on a lot of factors like the density of the water and the density of the air and the speed of the air and the depth of the water. So a lot of things contribute to the speed of the wave. The water molecules remain at the same positions on average. So that's what we're seeing here. What we're seeing here is the water molecules themselves are not propagating or traveling with the wave. They're basically just moving in tiny little motions locally where they are right now. And so actually I have a little example of that. Here is a stick in the water, and you can see as the waves come, the stick is just sort of moving up and down, and these little foamy things on the water as well are they're not moving with the wave, they're actually moving in circular motions, just like what is going on here. So anything that is floating in the water is also going to be approximately moving in these circular motions. Okay, so the surface waves produce a combination of longitudinal and transverse motion. So this is really interesting. And to clarify this, what I'm going to do is I'm just going to do a little review of longitudinal waves and transverse waves and surface waves, just to give you an idea of what that means. So this is more just a review. Hopefully you already know this, but if not, this is an important piece of the puzzle. So here we have longitudinal waves. So here's what they say about longitudinal waves. In a longitudinal wave, the particle displacement is parallel to the direction of wave propagation. So in this picture here, the wave is propagating from left to right, but the molecules are moving back and forth. So down here you see a better depiction of that, where you see the wave is propagating, but the particle, here's a little red dot here, the particle is moving from left to right. Each particle in here, although it is an optical illusion, makes it look like it's propagating, the actual molecules are just moving backward and forward. And so when we talk about longitudinal waves, we're talking about wave propagation, where the motion of the particles is in the same direction, is parallel to the direction of motion. So here we have transverse waves. So in a transverse wave, the particle displacement is perpendicular to the direction of the wave propagation. So here you can see the wave is propagating from left to right, but the molecules are moving up and down. The molecules themselves are not propagating with the wave, they are merely moving up and down. So for longitudinal waves, the particles move, left and right, and for the transverse waves, they move up and down, but the wave propagation is left and right. Water waves, water waves are an example of waves that involve a combination of both longitudinal and transverse motions. As a wave travels through the waver, the water, the particle travels in clockwise circles. So that's what I was showing you in the other animation. But so the particles are partly moving left and right, and they're partly moving up and down. So surface waves have a longitudinal component and a transverse component, and that's what makes these waves special. So the energy is carried by the waves towards the shore. Now this is another important point. I know there's a lot of confusion about what is energy and that sort of thing. So basically what's happening is the water waves are propagating and carrying the energy, but the energy doesn't manifest. The energy doesn't manifest until it hits the shore. Okay, so so the power of the wave does not manifest until it hits the shore. So let's look at a couple of examples here. So here's some video I took just a few days ago at Lake Huron, and the weather was really bad, and the waves picked up and were quite strong. And so the previous video I showed was also of Lake Huron, and you can see the waves aren't terribly high, but here we've got very strong waves. So the waves are propagating and they're crashing and creating a lot of power. Okay, so in this video here you can see I took the sound off. The wave crashed and it moved this log. Now this is a giant log. This log was the water has carried the log all the way along the lake. So a couple of years ago, this giant log, this is quite long, it's maybe 10, 12 feet long, 4 feet high, 5 feet high. It's almost as tall, like not quite as tall as me, but it's this is quite a big piece of wood, and this wave comes in and it can move it. And this log has been moving up the lake for a couple of years now, and the water is doing this. And so the idea here is that that is work. Okay, energy is often associated with work. Okay, energy is often associated with work. The energy, potential energy, is carried by the waves towards the shore, and it only becomes actual energy, which actually can move something, which can do work, when it crashes into something or the shore. So so that's an important thing about surface waves, or about any waves really, but I just wanted to make that point. And here's another really important point. The wind must be moving faster than the wave propagation speed in order to create the wave in the first place. So the wind must be blowing really fast in order for the waves to be created, in order for this circular motion to take place. So the wind is blowing from left to right, it's blowing faster than the wave propagation, and that is what is creating this circular motion. So this circular motion, this circulation, is the key to understanding Ionel's model, and because these circulating particles are analogous to the circulating water in Ionel's experiments. Okay, when you spin the cylinders, it makes the water circulate, and this water circulation creates pressure mediation between the objects, which either spreads them apart or brings them together. Okay, so this is going to be a very important point moving forward in this presentation. So the first thing I did was attempt to replicate the wave motion. So now this is the software that I wrote that creates the circular motion, and you can see that the waves, the pseudo waves, are propagating from left to right, and you've got circular motion, where you have big circles, and then as you go deeper and deeper, the circles get smaller and smaller. But one thing I want you to notice is that the angular rotation is the same for each of these circles. So the molecules travel each circle in the same period of time. Okay, so what this means is that the molecules on the bigger circle are physically traveling faster than the ones on the smaller circles. The radial motion is the same, but the tangential velocity would be much higher for the bigger circles. So that's just something to keep in mind. Okay, here's one. I did the same animation, only I made the circles bigger, and you can see I've got a higher wave amplitude. This really does look very much like the surface waves that you see on the water that I've been watching all summer at the cabin, and so this is a really good replication of that kind of mechanical wave. And then here's one more that I did with a very large circle, and you can see something interesting happening here where let me just play that again, where anyways you get a loop up here, and I believe this would be sometimes when you're watching waves and the waves crash long before they get to the shore, and that's because the wave amplitude has become too big. And I think what happens here is it pinches off, and then the water, because it's moving in this direction, would fall and crash in that direction. And so this is, you know, a very good replication of surface waves. So next what we did was we took that surface wave and we replicated it, we flipped it about a line, and this line now represents the wire. Okay, this is now getting into Ionel's model, where he models the ether. He models the ether as a wave around a wire. So let's just have a look at this for now. So what you see here is down here would be the surface wave that I was just showing you from the animation, and what I did was I flipped it 180 degrees, and now you have, so here you have the particles are circulating. Oh, I'm showing you a side view here. Let's go back to the beginning. So here you have counterclockwise circulation on top and clockwise circulation on the bottom, and so you have the wave propagating from left to right on either side of the wire. And so what I'm going to do is I'm going to show you my software directly rather than playing a video, because I think that'll be much more informative than just watching this video. So here's the model from my software. What we have here is the wire down the middle in this copper color, and what you have are these blue dots, and these blue dots represent the ether. Now I want to make a point here. In the paper, in Ionel's paper, what he does is he talks about two new substances from the periodic table. Okay, this actually was not his idea. This was a prediction made by Dmitry Mendeleev. I'm not actually sure how to say that right. Mendeleev, the inventor of the periodic table, basically made this prediction. He predicted that there should be two elements before helium in the inert gases as an inert gas. So these would be two additional inert substances that don't chemically react to anything. They are inert. And Dmitry Mendeleev called them X and Y for lack of a better name, but Ionel calls them ether and electrogen. So in my model here, I'm going to start the animation. Okay, so the blue dots correspond to the ether, and this would be analogous to the water in the surface wave analogy. And the yellow here corresponds to the electrogen, electrogen, and so basically generation of electricity. So you could call it electricity if you want to. So basically the idea is that the electrogen flows or blows, you can call it wind, the electrogen wind blows along the wire in the direction from left to right, from the negative to the positive, from the negative to the positive terminal, and propagates from left to right. So what it does, the wind blows, it causes the water, ether water, to circulate, just like in the water wave analogy. So that is what's going on here. And the wave, you can see quite clearly propagating down the line. And so it's this circulation is extremely important. Okay, this is actually what is causing the magnetic field in Ionel's model. So here I'm only showing you one intersection of the wire. I'm only showing you one cross section of the wire. Okay, so every cross section of the wire is going to show exactly the same circulation. And I'm going to set that up and show you what that looks like, but every cross section is going to show you the same picture here. So that's why I'm only showing one cross section. If I showed more cross sections, it looks a little bit confusing, but I'm going to set that up and show you what that looks like, just to give you an idea of that this is actually going on all the way around the wire, not just in one plane like that. So here I set up a model with many cross sections, and I'm going to show you the looking down the barrel of the gun view of the wire, and you'll see now I'm showing, you know, 1, 2, 3, 4, 5, 6 cross sections of the wire, and I will run the animation. It's going to be quite a bit slower now because I have way too many particles to show, but this will give you an idea of what it looks like in 3D. This is going on all the way around the wire, and so you can see why I didn't show you this view, because it is very confusing. Let's put the electrogen in there, and you'll see that you can still see the wave propagating through. You can see that it's happening all the way around the wire and not just in one plane. And of course there are more cross sections that I'm not showing because it would just be too time consuming to do the animation. So I just wanted to show you that, just to make sure you know that this is going on around the circle, not just in one plane along the wire. So here I'm just showing two cross sections. I'm showing two orthogonal cross sections of the wire because this is a little less confusing. I'm going to start the animation. So what you see here is you've got above the wire you have counterclockwise motion, and below the wire you have clockwise motion. So what is going on up here is opposite to what's going on down here. Now because this is circulation, this is like water, this is like a water vortex, this is like water circulating, which you can call a vortex. I refer to the wire as a bifurcator, as a bifurcation line, and above the wire and below the wire are vortex anti-vortex pairs. Now I know I've talked about vortex anti-vortex pairs before in other videos, and so this is an example of what one might call a vortex anti-vortex pair. So because they're circulating in opposite directions above and below the wire, I refer to them as vortex anti-vortex pairs because they come in pairs. You're not gonna you're not going to find circulation on one side of the wire and nothing going on the other side of the wire. You're going to find opposing vortices on either side of the wire, and no matter where you look, so I'm going to look at the orthogonal view 90 degrees, and you still see counterclockwise circulation down here, clockwise circulation down here. So no matter how you turn the wire, you're going to see counterclockwise circulation here and clockwise circulation here. Now here's an important point. There's an important point. If you are standing on the other side of the wire looking at me, you're going to see the opposite of what I see. Okay, you're going to see this. You're going to see the electrogen blowing from right to left. You're going to see clockwise above the wire, and you're going to see counterclockwise below the wire. No matter, so you're going to see clockwise above the wire, counterclockwise below the wire, no matter how you look at it. So when you turn the wire around, then you get the opposite view, but nothing has really changed. It's just your viewpoint has changed. This is the clockwise, counterclockwise mind meld, mind problem that that we run into all the time. And so we have to be very clear in choosing conventions when you're talking about this kind of thing, because otherwise you're going to say clockwise and I'm going to say counterclockwise, and we're both going to be right. And so I just wanted to kind of make that little point here that this is counterclockwise because I'm looking at it from this viewpoint, and you're going to see, you know, clockwise when you look at it from this viewpoint, right? So let's just keep that in mind, and I'll try to keep a common convention so that we're comparing apples to apples in this discussion. The other thing I want to point out here is that these circles aren't really circles. If you look at it from this perspective, you're going to think that they're just flat circles, but in fact these circles are cross sections of tubes that are surrounding the wire, of torus structures that are surrounding the wire. Okay, so I'm going to set that up, and I'm going to show you, I'm going to switch from showing the circles to showing the torus structures, and that should help to clarify that these are in fact the circulation is happening on the surface of a torus going all the way around the wire. So I'm going to set that up. Okay, so now instead of drawing the circles, what I'm doing is I'm drawing the toruses. Okay, and you can see the further you get away from the wire, the thinner the torus structures are. Okay, just like the circles were bigger closer to the wire as they get smaller as you get further away. So now I'm going to animate this. Let me tilt that a bit. Okay, so now I'm just going to tilt this a bit this way, and what you're going to see is that the water ether, the ether is circulating. The ether substance, these ether molecules are doing circular motions on the torus. Okay, so they're doing circular motion on the cross section of the torus. And of course I'm not showing all the molecules, I'm only showing a few of them, but you can imagine that this is going on all the way around the torus. So I am only showing two orthogonal views, but as you can see, all the molecules of ether are circulating in a circular fashion, not around the torus, but through the torus. Okay, that's going through, up, inside, outside, inside, outside. Okay, let's look at it from this view. Okay, so these circular torus structures are what we perceive as the circular magnetic field lines around that surround the wire. Okay, so these are analogous to, exactly equal to the circular magnetokinetic lines of force. These are the lines of force. So, but they're not really lines, they're tubes. I think others like Faraday used to call them tubes of force. These are literally tubes. They're tubes, and the ether circulates on the tubes and in this model. So I just want to point that out. Okay, let's look at it from this view. These radial lines would be the radial lines of that we see in the Steinmetz diagram, and these circular lines would be the circular lines that we see in the Steinmetz diagram. So what is the point of all this? What is it about this model that makes it special? Why do I think it's important? Why do I think it's a good model? And this goes back to the previous video that I showed you, where we saw that when you circulate water, when you spin cylinders which circulates water, you get attraction and repulsion. Basically, you mimic magnetism. What is magnetism? Well, magnetism is attraction and repulsion. Okay? Without attraction and repulsion, there's no point in magnetism. So magnetism is attraction and repulsion. And so in the previous video, I showed you experiments that Ionel did where he spun cylinders in water, and what we found was that if the cylinders are side by side and they're spinning in opposite directions, they attract. And when the cylinders are side by side and they're spinning in the same direction as each other, they repel. But if you have cylinders lined up axially and you spin them in the same direction, they attract. And when you line them up axially and you spin them in opposite directions, they repel. And so what I did was I made a little graphic that I'm calling the law of circulating ether. It's really the law of circulating fluid, but this is an ether model, so I'm really I want to talk about the ether in regards to this model. And so this little graphic shows that, you know, if the current, the electrogen is flowing in this direction from left to right, you're going to get counterclockwise circulation above the wire, and you're going to get clockwise circulation below the wire. And you may recall in let's see if I can find that video where Ionel defines the right-hand rule, where he says if the rotors turn in the direction shown by his fingers. Okay, no, that's not the right one. Should be the next one. Okay, this one here. So if the using the Fleming's right-hand rule, if you curl your fingers in the direction of rotation, your thumb is going to point to the North Pole. Okay, your thumb is going to point to the North Pole. And that's what he shows here. The light one was the North Pole and the dark one was the South Pole. And so this is the rule that I'm going to be using, only I'm going to use the right hand and the left hand because some people are left-handed and it doesn't really matter. So here what you find is if you curl your fingers in the direction of rotation, your thumb is going to point to the North Pole. So when I see counterclockwise circulation, I'm going to call that north circulation. And when I see clockwise circulation, so if you take your left hand and curl it in the direction of circulation, then your thumb is going to point to the South Pole. Okay, so this is the whole picture. This is the wire. If the electrogen is flowing, if electricity is flowing from left to right, then you're going to get north circulation above the wire, and you're going to get south circulation below the wire in the cross section that you're looking at. So in every cross section that you're looking at of the wire, this is what you're going to see. Now, if the electricity is flowing from right to left in this direction, you're going to get south circulation, clockwise circulation above the wire, and counterclockwise north circulation below the wire. So this is the standard that I'm using, that I'm developing, that matches Ionel's convention, and it also matches mainstream convention. Okay, and I'm just going to talk a little bit about induction, because I get a lot of questions about, well, you know, why do magnets cause iron filings to always attract? Okay, so this can be easily explained when you talk about it in terms of circulation. So if a cylinder, if the circulation is spinning counterclockwise, if you have a cylinder that is spinning next to a cylinder that isn't spinning, okay, if it has north circulation from your point of view, it's all based on your point of view. If you're looking down at the cylinders and they're spinning counterclockwise, the cylinder next to it is going to begin to spin clockwise, because this circulation here is going to cause this to circulate this way. So it is going to spin counterclockwise. And so this circulation is going to induce the counter circulation in the cylinder next to it. And as we saw in Ionel's experiments, when you have cylinders that are next to each other, that are spinning in opposite directions, they attract. Okay, so this is going to induce this one to spin such that it is attracted. It is never going to repel. And same with the south circulation. If the cylinder is spinning in a clockwise fashion and there's a non-moving cylinder next to it, it's going to induce counterclockwise motion. So this is going to be spinning clockwise. It's going to induce counterclockwise motion. This is going to pull it in this direction. And so you're going to get opposite circulation, and the cylinders are going to attract. Okay, so this is my convention that I'm going to be following to show you how, to explain why two wires attract or repel when you have current flowing through them. So here we have a two-wire situation. So now we have Ionel's model, but I have two wires next to each other. Okay, and this is an animation, not live, so I'm just going to play the animation, and what you find is that the circulation is counterclockwise above the wire, clockwise below the wire, counterclockwise above the wire, and clockwise below the wire. So the current is going in the same direction, the electrogen is going in the same direction. Between the wires you have clockwise circulation here, and counterclockwise circulation here. Let's do that again. So we have clockwise circulation here and counterclockwise circulation here. So these two circulations are next to each other, and as we saw with the spinning cylinders, when you have circulation, opposite circulation next to each other, it's going to cause attraction. So this model here can make a prediction, and the prediction is that if you have two wires next to each other and the electricity is flowing in the same direction, the wires are going to attract. Now, of course, we already know that this is true, but if we didn't know that this was true, this would be a prediction. And so this prediction, based on the actual experiments with spinning cylinders next to each other, is an accurate prediction, because we already know that if you take two wires and pass electricity through in the same direction, that the wires are going to attract. And so the other thing I want to point out is that this is counterclockwise circulation, so this is north circulation. This is clockwise circulation below the wire here, which is south circulation. This is counterclockwise and clockwise, north and south. So you can see, using using my convention here, you can also see that these wires will attract, because this is going to be a south pole and this is going to be a north pole, or south circulation, north circulation, and they attract. So this is a great way of looking at, I believe, attraction and repulsion and magnetism in terms of fluid dynamics and this ether model. So now we have a two-wire example again, only this time we've got opposite current. So we have electrogen going from right to left on the top, and we have electricity going from left to right on the bottom. And so between the wires you have counterclockwise circulation or north circulation, and above this wire you have counterclockwise circulation or north circulation. And so in this case we can make a prediction and say that, you know, according to Ionel's experiment, where you spin the cylinders in the same direction and you get repulsion, here as well you're going to get repulsion. And this is analogous to having two north poles next to each other. And so obviously that is going to create a repulsive situation. So that's all I'm going to say right now about this model. I highly recommend that you read the rest of this paper if you haven't already. I will leave a link to it in the description of this video. I'm sure I will have more to say about this in the future, but I think this is enough information for you to have to absorb all at once. If you have any questions, please feel free to ask me. I really think this model is very special. It fits in nicely with my Aether model. I understand it. You've got experimental evidence to back it up. It is a very strong model, and I think that it is definitely worth further investigation. And so thank you very much, and have a great evening.